Hello everyone, welcome back. Texas Little Apple is here, and we're starting math class right now. Compare these two numbers. 2 cubed, and 3 squared. Which one is bigger? You'd probably pick 3 squared, without thinking. Now let me push this one step further. What happens when the numbers grow? For example, 15 to the 16th power versus 16 to the 15th power. Which one's bigger? Most people pick 16 to the 15th power, it has the larger base, 16. But that instinct is usually wrong. Can we prove this without a calculator? And do it in under 60 seconds? First, we're comparing 15 to the 16th power and 16 to the 15th. Which one is bigger? Let's start with a smart method using ratios. Set up the comparison by forming the fraction. 16 to the 15th over 15 to the 16th. Rewrite the denominator as 15 to the 15th times 15. Now factor the powers. This becomes 16 over 15, all raised to the 15th power. Times 1 over 15. And notice that 16 over 15 is just 1 plus 1/15. Now we're ready to estimate this, without a calculator. Step 2, Inequality Substitution. Notice that 1 plus 1/15 is less than 1 plus 1 over n, for any n between 0 and 15. So we can squeeze the first 13 terms. That gives us this comparison. 1 plus 1/15, raised to the 15th power, times 1 over 15, is less than the product. 1 plus 1/14, 1 plus 1/13, all the way down to 1 plus 1/2, times 1 plus 1/15 squared, times 1 over 15. Now we're ready to compare sizes. Step 3, Telescoping cancellation. Now look at this product. 1 plus 1/14. 1 plus 1/13. All the way down to 1 plus 1/2. Rewrite each term as a fraction. That gives 15 over 14. 14 over 13. 13 over 12. And so on. Everything cancels in a telescoping chain. What's left is simply 15 over 2. Now we can finish the comparison. Step 4, the final comparison. From the previous steps, we compare 1 plus 1/15, raised to the 15th power, times 1 over 15, with an upper bound. That upper bound simplifies to 15 over 2, times 1 plus 1/15 squared, times 1 over 15. When we simplify, this becomes 128 over 225, which is less than 1. That means 16 to the 15th divided by 15 to the 16th is less than 1. So the conclusion is clear, 15 to the 16th power is greater than 16 to the 15th. Bigger exponent beats bigger base, this time. Next, we scaling up, apply the same logic to 100 to the power of 101, and 101 to the 100th. Set up the comparison by forming the fraction, 101 to the power of 100 over 100 to the power of 101. Rewrite the denominator as 100 to the 100th, times 100. Now factor the powers. This becomes 101 over 100, all raised to the 100th, times 1 over 100 inch. And notice that 101 over 100 is just 1 plus 1 over 100. Now we're ready to estimate this, without a calculator. Step 2, Inequality Substitution. Notice that 1 plus 1 over 100 is less than 1 plus 1 over n, for any n between 0 and 100. So we can squeeze the first 98 terms. That gives us this comparison, 1 plus 1 over 100, raised to the 100th, times 1 over 100, is less than the product. 1 plus 1 over 99. 1 plus 1 over 98. All the way down to 1 plus 1/2, times 1 plus 1 over 100 squared, times 1 over 100. Now we're ready to compare sizes. Step 3, telescoping cancellation. Now look at this product. 1 plus 1 over 99. 1 plus 1 over 98. All the way down to 1 plus 1/2. Rewrite each term as a fraction. That gives 100 over 99. 99 over 98. 98 over 97. And so on. Everything cancels in a telescoping chain. What's left is simply 100 over 2. Now we can finish the comparison. Step 4, the final comparison. From the previous steps, we compare 1 plus 1 over 100, raised to the 100th, times 1 over 100, with an upper bound. That upper bound simplifies to 100 over 2, times 1 plus 1 over 100 squared, times 1 over 100. When we simplify, this becomes 0.51005, which is less than 1. That means 101 to the power of 100, divided by 100 to the power of 101, is less than 1. So the conclusion is clear: 100 to the power of 101 is greater than 101 to the power of 100. Here's the key mathematical rule. For any two positive numbers a and b, comparing a to the power b, and b to the power a, is equivalent to comparing a to the power 1 over a, and b to the power 1 over b. First, let's analyze the function f of x equals x to the power 1 over x for x greater than 0. Using calculus, we can determine where this function is increasing or decreasing by examining its derivative. The function, x to the power of 1 over x, reaches its maximum value at a critical point, where x equals e. Here, e is approximately 2.718. For values less than e, the function, x to the power 1 over x, is strictly increasing. And for values greater than e, the function, x to the power 1 over x, is strictly decreasing. The graph shows this clearly. The curve peaks exactly at x equals e. This is why comparing exponents works this way. Now let's apply this rule to 15 and 16. Both 15 and 16 are greater than e. Since x to the power of 1 over x is decreasing for values greater than e, we get 15 to the power of 1 over 15 is greater than 16 to the power of 1 over 16. Raise both sides to the power of 15 times 16. This gives the result. 15 to the 16th power is greater than 16 to the 15th. Now applying the rule to 100 and 101. The same logic works again. Both 100 and 101 are also greater than e. So 100 to the power of 1 over 100 is greater than 101 to the power of 1 over 101. Raise both sides to the power of 100 times 101. And we conclude, 100 to the 101st power is greater than 101 to the 100th power. So when both numbers are greater than e, the smaller base with the larger exponent wins. Now let's apply this rule in general. Consider any number n, and the next integer n plus 1, where n is greater than e. Since the function x to the 1 over x is decreasing for values larger than e, we get this inequality: n to the power of n plus 1, is greater than n plus 1 to the power of n. The graph of x to the power of 1 over x explains why this always holds. So for any n greater than e, n to the power of n plus 1 will always be larger than n plus 1 to the power of n. Bigger exponent beats bigger base, once you're past e. To summarize, we explored two complementary approaches. First, we used a non-calculus method, relying on elementary algebra together with a hybrid of squeezing and telescoping products, to establish a clean upper bound. Then, we moved to a more advanced perspective, using the function x to the power 1 over x, and the constant e to uncover a powerful general rule. Along the way, you discovered several key ideas. The ratio test, breaking massive exponents into manageable fractions. The hybrid squeeze, simplifying products by tightening some terms while keeping others exact. Scaling up, applying the same logic to larger examples to reveal a consistent pattern. And the role of e, explaining why n to the power of n+1, eventually dominates n+1 to the power of n, once we pass the critical threshold e. Whether you're preparing for competitions, like the AMC or IMO, or you simply enjoy a good numerical puzzle, this is a powerful technique to add to your mathematical toolkit. And if you enjoyed this deep dive, don't forget to like and subscribe for more explorations into elegant mathematical ideas. Alright, it's time to wrap up. Leave a comment below, and don't forget to like, share, and subscribe for more fun math problems. See you next time, and thank you for watching.